Hello everybody, welcome into another lesson. So today we are going to talk about a couple of examples that put the idea of average rates of change or the slope of a secant line and the instantaneous rate of change or the slope of a tangent line into real world applications. So let's say I have something like a tank holds 1,000 gallons of water, which drains from the bottom of the tank in 30 minutes. So it started with 1,000 gallons of water at 0 minutes. By the time you hit 30 minutes, there's 0 gallons left. So these values in the table here show the volume of water remaining in the tank after so many minutes. The volume denoted by V, the time t. You can find what's called an average rate of change between two times by applying the idea of the slope of a secant line. If we recall from yesterday's lesson, the slope of a secant line simply equals f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. If we apply that to this particular problem, the table gives us these various values here. The f of x sub 2 would be v sub 2, which is the volume, the second volume minus the first volume, divided by the second time minus the first time. And you would get your answer in gallons per minute, being a rate of change. So rates of change such as gallons per minute, such as miles per hour, kilometers per hour, meters per second, so on. Those are units for rates of change. You usually take it with respect to time. You have something changing with respect to time. Now, if I wanted to find the instantaneous rate of change at one of these times, I'm going to need to find the slope of two secant lines at that time, around that time, the same width apart. And then I'm going to need to define the slope of that tangent line, the instantaneous rate of change. I just average the slope of the two secant lines and I'll still get an answer in gallons per minute. So let's do a couple of problems with this. So let's see here. Let me start out with find the instantaneous rate of change at 5 minutes. So we really want to find the instantaneous rate of change when the time equals 5. Well, we don't really have a function. This is a function, but we don't have a function in the form of f of x equals a certain function. So we're relying on a table of numerical values to do that for us. Again, if we recall, if we want to find the instantaneous rate of change, which is the slope of the tangent line, we first need to find the slope of two different secant lines that include that time 5 in that interval. So let's find the slope of the first secant line. Why don't we take from the time t equals 5, so we will take then f of 5 minus f of 0, because that's 5 units apart from 0, and then the next one we'll take f of 10 minus f of 5. You want to be the same amount of x units apart. So we'll take f of 5 minus f of 0 all over 5 minus 0. Well, that's going to, of course, at 5 minutes, that's our time, the volume in the tank is 694 minus f of 0. Well, at time 0, though it's not listed here, in the problem it tells you that the tank holds 1,000 gallons. So right at 0 minutes, there are 1,000 gallons in the tank. So f of 0 is 1,000. All that divided by 5 minus 0. Well, this should end up coming up to negative 306 divided by 5. So we should get negative 306 divided by 5, which for all intents and purposes will round to 2 decimal places for this secant line, for this average rate of change. So if we take negative 306 and divide it by 5, you get about negative 61.2 gallons per minute. And it actually makes sense that we have a negative rate, because if water's draining from the tank, you're going to be going down gallons, right? If we were filling the tank, we'd have a positive value, but we're actually losing water out of the tank, so we're going to have a negative value for our rate of change, for the average rate of change between 0 and 5 minutes. Now, what we should do next is, if we want to find the instantaneous rate of change, we should probably take the slope of the secant line from 5 to 10. It's also 5 units apart, but to the right of 5. So let's go ahead and let's take the average value, the average rate of change from 5 to 10 minutes. So this would be f of 10 minus f of 5 divided by, now that's going to be divided by 10 minus 5, which would end up then giving you f of 10, which is t minutes, would give you 444 gallons, minus your 5, f of 5, that's 694 gallons, divided by 5. Well, that's going to give you negative 250 divided by 5, which would give you a rate of exactly negative 50 gallons per minute. So the average rate of change from 5 to 10 minutes is negative 50 gallons per minute. So we have found 2 average rates of change that both include the time t equals 5 minutes and that are equally distant apart. You have from 5 to 0 for your first secant line, and then you have from 10 to 5 for your second. They're equal distant apart. That's very important. Otherwise, you're going to get skewed results. Now, if we want to find the instantaneous rate of change, that's going to be the slope of the tangent line, m sub t. All we need to do now is add these 2 slopes of the secant lines together. So negative 61.2 plus, or actually in this case it'd just be minus 50, divide all that by 2, you end up then getting negative 111.2 divided by 2, which, let's go ahead and divide that. So let's see, negative 111.2 divided by 2 gives you about negative 55.6 gallons per minute. So to recap this, and this would actually be our instantaneous rate of change at time equals 5 minutes. So from 0 to 5 minutes, we found the average rate of change to be minus 61.2 gallons per minute. And then from 5 to 10 minutes, we found the average rate of change to be minus 50 gallons per minute. Now, again, 0 is 5 units away from 5, 10 is 5 units away from 5. We want to take equidistant t values away from 5, so you get an accurate result. Then we found the instantaneous rate of change simply by averaging these two rates of change. And your instantaneous rate of change at time being 5 minutes is about negative 55.6 gallons per minute. That's how much water it's losing at that time. Now, what if, let's change this a bit here. What if this time I wanted to find it at 20 minutes? So let's say I find the instantaneous rate of change at 20 minutes. That's exactly what I want to find. At 20 minutes, I want to find the instantaneous rate of change. Well, again, what I need to do first, for now at least, until we get other formulas later on in the course, I need to find the slope of two secant lines, or two average rates of change for equal distance around 20 that include 20 in that. So I should probably first go from 15 to 20. If I want to find the average rate of change from the time 15 minutes to 20 minutes, because we need to include 20 minutes in our average rates of change since we're going to find the instantaneous rate of change. So if I want to go from 15 to 20 minutes, I will take f of 20 minus f of 15, divide that by 20 minus 15. Now at 20 minutes, this tells me I have 111 gallons in the tank. Then at 15 minutes, I have 250 gallons in the tank. So 111 minus 250, the numerator turns into, divided by 20 minus 15. I end up getting negative 139 divided by 5, which, let's go ahead and do that. So negative 139 divided by 5, that's negative 27.8 gallons per minute. So my tank is, the average rate of change from the time being 15 to 20 minutes for those 5 particular minutes is about negative 27.8 gallons per minute. Now, in order to find the instantaneous rate of change at 20 minutes, I need to take the slope of another secant line that's also 5 units apart from 20. This time will go to the right. That would definitely be time t equals 25. So from 20 to 25, that's going to be f of 25 minus f of 20 divided by 25 minus 20. Well, at 25 minutes, I have 28 gallons left in the tank. Minus at 20 minutes, I have 111 gallons left in the tank. All that divided by 25 minus 20, which would end up giving me negative 83 divided by 5. So let's go ahead and take that. Negative 83 divided by 5, you get approximately negative 16.6 gallons per minute from 20 to 25 minutes. Your average rate of change is about negative 16.6 gallons per minute. So now we have the slope of two secant lines based off of times equally distant apart from time 20. Now if we want to find the instantaneous rate of change at time 20 minutes, we just need to take, that's going to be the slope of the tangent line at time equals 20, which is the average of these two secant lines. So m sub 1 plus m sub 2 divided by 2, well, the first secant line slope is negative 27.8, that'd be plus negative 16.6. So this would be minus 16.6 divided by 2. So what do you get here? Let's take negative 27.8 minus 16.6. You get negative 44.4 divided by 2, which would end up giving you a rate, instantaneous rate of change of negative 22.2 gallons per minute. So that's the answer. At 20 minutes, the instantaneous rate of change is going to be, you're losing water at a rate of negative 22.2 gallons per minute. Well, notice before, between when we did it for 5 minutes, we were losing at over 55 gallons per minute. Now we've slowed down to over 22 gallons per minute at time 20. This also illustrates how we don't have constant rates of change. The rates of change themselves vary as you go further along. And there could be many factors contributing to that, such as gravity, such as any surface tension, such as the shape of the tank, all those kind of things. In the real world, such as this, it's not some simple algebra formula for slope where the slope of the line is constant. This is definitely a nonlinear function that we're finding instantaneous rates of change and slope for. So that's just one practical example. Now I have a medical example which I think is really cool. We're going to do a medical example. So let's see here. How's this set up? Just bear with me a minute, I'll change everything here. At least the TB in minutes stayed the same, but I don't want to completely destroy my table, so alright, so the top row belongs to minutes, the bottom row is the number of heartbeats. So yes, we're going to be talking about heart rate for this particular example. So let me just build the table. Whoops, that's 36, not 26. Excuse me. 36, we had 2,530 heartbeats. At 38 minutes, we had, let's see, 2,661 heartbeats. 40 minutes, we had 2,806 heartbeats. And then let's see, at 42 minutes, we had 2,948 heartbeats. And then last entry is at 44 minutes, we had 3,080 heartbeats. Alright, so that means I can delete the far right column of this table then. So what does the problem say? A cardiac monitor is used to measure the heart rate of a patient after surgery. It compiles the number of heartbeats at T minutes. Alright, so this problem here is about a cardiac monitor is used to measure the heart rate of a patient after surgery. It compiles the number of heartbeats at T minutes. So here you have times T in minutes from 36, 38, 40, 42, and 44. And then in the row below, that's just the number of heartbeats at those given times. Now keep in mind that is not the rate. If you had a heart rate of 2,530 beats a minute, you'd be dead well before you even reach that. This is just the number of heartbeats themselves, okay? Now, I'm going to throw a couple of these out here. Find the heart rate find the instantaneous change in heart rate at 38 minutes. Alright, so we want to find the instantaneous change in heart rate at 38 minutes. The instantaneous should clue you in that we're talking about the slope of a tangent line. That's what instantaneous change is. It's going to be the slope of a tangent line if it's instantaneous. If it's average, that means secant. Well, for now, all we have to find an instantaneous change are taking the average of the slope of two secant lines. But before too long on the course, we'll get other tools. But if we want to find that time at 38 minutes, we need to find the slope of two secant lines that contain the time 38 minutes. So we should probably pick our first secant line to be from 36 to 38 minutes. So if we find the slope of from 36 to 38, well, this is going to be f of 38 minus f of 36 divided by, then at 38 minutes you had 2,661 heartbeats themselves, minus at 36 minutes you had 2,530 heartbeats themselves. Wait, hold on a minute. I'm prematurely filling out my numerator values. I want to take f of 38 minus f of 36 divided by that 38 minus 36 itself. Now at 38 minutes you had 2,661 heartbeats, minus at 36 minutes you had 2,530 heartbeats. All that divided by 38 minus 36, which would then, let's see what that simplifies into. That should be 131 divided by 2, which would be approximately 66.5 beats per minute. Which I'm pretty sure is abbreviated in the medical community BPM. Not BMP, BPM. So from 36 minutes to 38 minutes, the average heart rate was 66.5 beats per minute. Now, again, the goal is to find the instantaneous heart rate at 38 minutes. I should probably just say instantaneous heart rate at 38 minutes. Well, if we want to find the instantaneous heart rate, we found the slope from 36 to 38. We should probably take one from 38 to 40, since it's equidistant apart. So let's find the average heart rate from 38 to 40 minutes. So that's going to be f of 40 minus f of 38 divided by 40 minus 38. So at 40 minutes, this heart monitor measured 2,806 beats, minus at 38 minutes, it measured 2,661 beats, divided by 40 minus 38. Well, that's going to give you, let's see here. So 2,806 minus 2661, that's 145 divided by 2, which is approximately equal to 72.5 beats per minute. So from 38 to 40 minutes, the average heart rate was 72.5 beats per minute. Now, if we want to find the instantaneous heart rate at 38 minutes, we need to take the average of these two average heart rates. So I'll put that in the red ink. That would be the slope of your tangent line. That's going to equal that first average heart rate of 66.5 plus your second heart rate average, which was 72.5, all that divided by 2, which, let's see what you get here when you add the numerator. So 66.5 plus 72.5, you get 139 divided by 2, which would be approximately 69.5 beats per minute. So your average heart rate at 38 beats per minute, your average heart rate at the time 38 minutes is approximately 69.5 beats per minute. Now, some people would think, well, okay, couldn't you just take the number of heartbeats themselves? Not necessarily something you want to do. Let me divide that real quick. Because you get an inaccurate result. You get about 70.0263, which isn't too far off, but that doesn't really show you the rate of change. That doesn't really show you the full picture of the instantaneous heart rate. And that would actually skew your results if you took the number of heartbeats, divided it by the time itself. So you're better off to find yourself a couple average rates of change and then average those, as long as you include that same time in both of those. Now, what if this time we find the heart rate at the time 42 minutes? Find the, let's see, so we're going to find the heart rate at 42 minutes. So we want to find the heart rate at time being 42 minutes. Well, again, what's probably the best thing to do is take the slope of two secant lines, or in other words, find two average rates of change that both of those contain time 42 in it. Well, let's go to the left of 42. We should probably do time 40. So if we want to find the slope of the first secant line, or the first average heartbeat, the average heart rate, we should probably take from time 42 to 40, so that would be f of 42 minus f of 40 divided by 42 minus 40 itself. Well, at 42 minutes, we have 2,948 heartbeats, minus at 40 minutes, we have 2,806 heartbeats, divided by 42 minus 40. Well, this would end up giving you 142 divided by 2, which would be exactly 71 beats per minute. So the average heart rate from 40 to 42 minutes ended up being 71 beats per minute. Now, of course, we want to find the heart rate, which really means the instantaneous heart rate at time 42 minutes. We should probably take a second secant line slope, or a second average heart rate. This time, let's go from 42 to 44. So to find that second average heart rate, this will be f of 44 minus f of 42 all over 44 minus 42. Well, at 44 minutes, there were 3,080 heartbeats, minus at 42 minutes, there were 2,948 heartbeats. Divide all that by 44 minus 2. 44 minus 42. That's going to equal then, let's take 3,080 minus 2,948. That's going to end up then being 132 all over 2, which would be 66 beats per minute. So, I forgot the B. So your average heart rate from the time 42 to 44 minutes is 66 beats per minute. Now, if we want to find the instantaneous heart rate at time 42 minutes, we should take the average of these two average heart rates, and then we should be able to get that. That's the same as the slope of the tangent line. So that's going to equal the slope of your first secant line, or the slope of your first average, which would be the first average heart rate, plus your second average heart rate, divided by 2. So that should end up giving you 137 divided by 2, which is what? What is 137 divided by 2? That's about 68.5 beats per minute. So the average heart rate at 42 minutes is about 68.5 beats per minute. That's a pretty, I mean, I'm not a medical expert, but I would say that's a pretty good pulse, especially having just come out of surgery. That's actually pretty good. But anyway, so those are a couple of real world examples where we want to find average rates of change, the slope of the secant line, and then use those to find the instantaneous rate of change, the slope of the tangent line. So that's it for this lesson. Next lesson we're going to get into something called one-sided limits. So I hope everybody has a great day. Take care.